For the last couple of years, I have been programming in C#, a popular high-level language. But the more I develop, the more curious I have gotten about the actual operations happening at a lower level of the machine. I decided to explore the world of transistor logic gates as the closest approximation for what happens in the circuitry of a computer when you as a person use it. Now, transistors are large enough to see with your eyes, but your computer is running millions and millions of these operations on a microscopic scale inside your machine as I speak. Let's together look at some of the basic operations of a computer. I will also show the logic represented by code, this time in Python for readability. What you're seeing is me building the simplest logic gate. It is called a buffer. This works as you would expect an ordinary switch to work. Let me explain. A transistor is like a gate. It can either allow or block electricity to flow through it. You control this gate by providing a current to the so-called base pin of the transistor. If no electricity is applied, then the transistor is blocked. In this case, pressing the button provides a current to the transistor, opening the gate, allowing electricity to pass through and continue to the LED, thereby lighting it up. This can be represented in code as if button pressed is true, then we will print to the console that the LED is lit up. All other cases will print that the LED is dark. An inverter, as the name suggests, works opposite to how a buffer or switch would work. By default, the LED is lit, but when the button is pressed, it turns off the LED. If you've ever played around with electronics, you most likely have at some point short-circuited your setup, meaning you allow electricity to go straight to ground without passing through your components. In essence, that is what the button does in this configuration. It short-circuits, interrupting the flow of electricity to the LED, and as a result, the LED switches off. The code representation is very similar to the previous one, but this time, when the value is true, the LED will be dark instead. Okay, so now the fun begins. We will now be using two transistors. The AND gate represents a setup where two inputs must be true in order for it to output a signal. In this case, we have to press both buttons for the LED to light up. The way we do this is by first building two buffers, but instead of the output of the first transistor, or emitter as the pin is called, going straight to the LED, it goes to the input or collector pin of the second transistor. This put the transistors in a serial setup, one after the other. The second transistor then outputs its current to the anode of the LED. The base, that is, the pin that controls whether the transistor will allow current through, of both transistors are connected to their respective button, thus needing both buttons to be pressed to complete the circuit. In code, this would be like a nested if statement. As you can see, to reach the innermost code, both values must be true. In code, you can of course simplify the whole statement to So the OR gate requires that at least one of the buttons is pressed in order for the LED to light up. If you think about it for a while, a buffer was the basic switch function. So an OR gate is just two buffers outputting to the same LED. If we connect the transistors in parallel, we can achieve the setup where as long as at least one button is pressed, a circuit is completed, letting current flow through the LED. As you can see, when we press both buttons, the LED lights up, since the condition is that at least one of the buttons is pressed. Keep this little detail in mind for later. OR gates in code can be represented by using two if statements. And just like the previous AND gate, it can be simplified like this. In a NAND gate, which is an inverse of the AND gate, pressing 2 buttons should shut off the LED instead of lighting it up. Well, remember how the inverter we built earlier, the one where if you press the button it switches off the LED by short-circuiting the circuit? We can do the same here, but instead of 1 button, we connect 2 buttons in serial, which when pressed creates a pathway for the electricity to go to ground without having to go through the LED. And the code is almost identical to the AND, except this time we're checking they are false instead of true. Ah yes, the XOR gate, the bane of my initial progress when learning about logic gates. I told you earlier to keep in mind that in a regular OR gate, if both buttons are pressed, the LED should light up, because in an OR gate, the requirements is just 1 button. And if both buttons are pressed, then at least 1 button has been pressed. That is not the case for XOR. The X in XOR stands for exclusive. Now, if you want to learn some fancy language for concepts you probably already understand, I could point you to the Wikipedia article about logical biconditional. In more everyday words, you could describe the function as if and only if 1 button is pressed, the LED should light up. So, with our XOR gate, we should only see the LED light up if 1 of the buttons is pressed. If none of the buttons, or if both buttons are pressed, the LED should remain off. As you can see, to make this work, we've had to dramatically increase the amount of transistors and wires. So let's see if we are successful. And it works. You can probably also see it does give like a short blink when I press both buttons as well as when I release them both. I'm not sure why this happens, if it's because I don't press the buttons simultaneously enough or if it's because of my wiring somehow. Writing this in code means you have to check if green is true and red is false, or that red is true and green is false, which will require 2 different nested if statements. Now I have chosen to simplify it like this. The computer is a remarkable machine. Built upon these very basic, almost trivial operations, enormously complex activities are possible. If you combine enough of these logic gates, you will have all the operations of a modern-day computer. Whether it's sending emails to your colleagues, playing Minecraft, or like I stated earlier, watching this very video. Regarding watching this video, thank you for staying till the end. I hope it was at least a fraction as exciting to you as the exploration and building of these logic gates were to me.